Hello, welcome to MDM4U Grade 12 Data Management Lesson 1.4, Mutually Exclusive Events and Non-Mutually Exclusive Events. Our learning goals today are to be able to describe how an event can represent a set of probability outcomes, to recognize how different events are related, and to calculate the probability of an event occurring. So when calculating a probability of either one event happening or the other happening, it's really important to carefully count the outcomes. When two events have completely different characteristics, they are said to be mutually exclusive events, which means that one event can happen or the other event can happen, but both can't happen at the same time. So in other words, to calculate the probability of the mutually exclusive events, we're going to use the additive principle. So what do I mean? So let's take a look at, let's suppose we take a look at eye color, right? So we'll label this up eye color. And we're going to use something called a Venn diagram here to the right. So this is not a picture of two eyes. This is a Venn diagram that basically the circles represent a set of something. So let's have a look at the event A, that the color of eyes are brown, and B, that the color of eyes are blue. Now when I do this in class, I might just ask you who has brown eyes, who has blue eyes, and then we'll get some figures. I'm just going to make it up for now. I'm going to suppose that we have 7 brown-eyed students in class, and we have 6 blue-eyed students in class. And then you might say, well, hang on a minute, Mr. Hooker, there's some green-eyed students in class or grey-eyed students in class. Yeah. Okay, so let's deal with that with anything outside these circles. So if they're not brown-eyed or not blue-eyed, we'll put them outside here. 6 students that have eye colours other than brown or blue. So let's have a look at labeling up using mathematical notation. Our number in our sample space, complete sample space, is how many students. So we have 7 with brown eyes, 6 with blue eyes, and 6 with others. So let's just add those up. 7 plus 6 plus 6 is 19. Now let's have a look at the number of people with brown eyes, which we gave a letter A. Number of people with brown eyes was 7. And the number of people with blue eyes was 6. And there we go. Okay. Now, I hope you agree. If you've got brown eyes, then you have brown eyes. You can't possibly have blue eyes at the same time, or another color of eye at the same time. These are mutually exclusive events. So the additive principle for mutually exclusive events basically means that the probability of either of two mutually exclusive events, A or B, we can add them together. So the probability of having either brown eyes or blue eyes is simply 7 out of 19 for brown eyes plus 6 out of 19 for blue eyes, which gives me a total probability of 13 out of 19. So approximately, put that in your calculator, put the little dot on top of the equal sign to show that you've rounded it, 0.684 or 68%. Okay, so 68% chance that someone in my class has brown or blue eyes, and that's it. All right. So let's have a look at another kind of event here. So a standard deck of playing cards is represented below, and we want to look at the probability of drawing a red face card or a black ace, and we're going to draw a Venn diagram to illustrate. So let's highlight what that would look like. So a red face card, that means it's either a jack, a queen, or a king, and it's one of these, right here. Jack, a queen, or king in hearts or diamonds, or it could be a black ace, which I think there's only 2 of over there. Now you'd agree that those are mutually exclusive, can't be both at the same time. All right, and let's draw a Venn diagram. I think we've got space on the next page. I did make it on the next page, yes. So let's first of all count up our sample space. So we know that in our sample space we have how many cards? 52 in the total sample space. Good. And the number of red face cards, let's call it RFC, is 6. and the number of black aces is 2. Agreed? So therefore, the probability of drawing either a red face card or a black ace card is the probability of the red face card added to the probability of the black ace card, which is simply 6 out of 52 plus 2 out of 52. Why? Because I have the number of red face cards here is 6 out of my sample space size, which is 52, plus my number of black ace cards here, again divided by my sample space of 52. And that together will give me 8 out of 52, which reduces to 2 out of 13, or approximately 0.154, or 15.4%. Okay. And let's draw a little Venn diagram to illustrate that. So here's my Venn diagram. This box represents my sample space, which has 52 cards in it in total, right? So we could have a look at a red face card, which we know there are 6 of. And we could have a look at our black ace, and they don't overlap. Those two circles do not overlap because it can't be both at the same time. And we have 2 of those. And out of 52 cards, then the rest of them are not red face cards and they're not black aces. So that goes on the outside. And so we've got 52 minus 8, which gives me 44 cards left over. And that would be a Venn diagram illustrating it. In some situations, it's possible for different events to occur simultaneously. So when the 2 events have some characteristics that are the same. So they are what we call non-mutually exclusive. So when they're non-mutually exclusive, let's think about this. So we could have something like, how about diamonds? Diamonds, which we'll call D, and the face cards. So again, using my same deck of cards, right, we can take a look and we'll say to ourselves, well, hang on a minute, how many diamonds are there? Well, I know that there's 13 in each suit, so I know that my sample space for diamonds is 13. My sample space for face cards, let's count the face cards, we've got 3, 6, 9, 12 of them. But some of them are overlapping, because you'll see we have 3 of those which are diamond face cards, right? They're both diamonds and face cards. So let's do it like this. So let's put our diamonds here, our face cards here. Now you'll see that my 2 circles are overlapping. Now starting from the middle bit, I know that both diamonds and face cards, we know we have 3 of them, right? But my face cards, oh sorry, I'll start with diamonds first. My diamonds, I only have a total of 13. So you need to take a look at this. So this is my diamonds. This represents diamonds right here. I've already accounted for 3 in there. So therefore there are 10 diamond cards that are not face cards. And likewise, we can take a look at the face cards, and we know that 3 of them are diamonds, right? So therefore, the other 9 of them are not diamonds. And that's what it looks like there, okay? And then on the outside of that, well, what are not diamonds and not face cards? Well, if we don't have diamonds, we don't have face cards, we have everything that's left, which will give us 10, 20, 30, I think it is, 30. But we can check that and make sure that these values here add up to 52. 30 plus 10 is 40, 49, 52. Good, okay? So that's what we call non-mutually exclusive, right? And I'll write this down for you. So they are non-mutually exclusive. Okay, so for a standard deck of cards, how many ways could you draw a diamond or a face card? So that's the Venn diagram to draw the favorable outcomes, right? What is the probability of drawing a diamond or a face card? So the probability of drawing a diamond or a face card is simply equal to, let's have a look. So we've got the probability of drawing a diamond, right, plus the probability of drawing a face card. And we know that we have these values here to help us with that, right? So we have diamond is 13 of them out of 52. We know that face card is 12 out of 52. But we have to subtract from here the outcome when they both happen. So we have to subtract the probability of a diamond face card, which we know from our Venn diagram here is 3. Because otherwise we'd be counting it twice. So that would simply equal 22 out of 52, and I think that is a decimal is something like 0.423 or 42.3%. Okay? So when they are non-mutually exclusive, it's really important that that we account for double counting. So we have to use this formula and make sure that we use a principle of inclusion and exclusion, or the additive principle, which can be determined using this formula. All right. So that is it. So just make sure that you don't double count when the two events have characteristics that are the same. So let's take a look at something where it's not so familiar to you as a pack of cards. And here we go. In a room with 30 students, 10 play basketball and 15 play volleyball. If 7 students play both sports, how many play basketball or volleyball? It's one of those lovely questions. So we could start off by doing a Venn diagram if you like. So we have basketball students, we'll call B. And we know that 10 play basketball, we know that 15 play volleyball, but 7 students play both. When you see the word both, you know that you're going to have non-mutually exclusive events. So let's start out by putting our both of 7 in there. All right, now let's focus on our circle with basketball right here. And I'll use a red pen. So basketball, which is this circle on the left, we need to total up to 10. Well, we already have 7 in that shared piece, so we only have 3 left over to put there, right? And then we'll do the same with volleyball, and for that I'll use a blue color. So volleyball is this right-hand circle there. 7 play both volleyball and basketball. So the remaining, which is, mental math, there we go, 8, will play just volleyball. So now let's add those together. 3 plus 7 is 10, plus 8 is 18, and there's 30 students altogether. So that means 12 students play neither basketball or volleyball, right? So let me explain again. There's 12 we got from our 30 students minus the 18 that we know play either basketball or volleyball or both. Okay, so let's formalize this mathematically now. So the number of basketball or volleyball players, right, is the number of basketball players plus the number of volleyball players minus the number of basketball and volleyball players. So if you prefer the mathematical approach first rather than the diagram, fine. So the number of basketball players is 10, the number of volleyball players is 15, and the number that play both is 7. And then when we do that math there, we get 25 minus 7, which is 18. So we know that 18 play both. Sorry, basketball or volleyball or both. Okay? To calculate the probability of either non-mutually exclusive events A or B occurring, we use the additive principle for non-mutually exclusive events. So you'll see the formulas are very similar. The probability formula is very similar to the counting formula. All right. So what do we do if it's a little bit bigger than that? What if we got 3 events, right? So let's take a look. What if we have an event A, B, and C? What about that? And what if they all overlap? Let's take a look. 1, 2, and 3. Okay. So the number for A or B or C, when we're counting, we're going to count all the A's, we're going to count all the B's, and we're going to count all the C's. Makes sense, right? We'll count all the A's, we'll count all the B's, we'll count all the C's. But when we've done that, bear in mind that we will have counted this segment twice, right? So therefore we need to, actually we've counted this segment twice, right? This segment, so the A's and the B's will have counted twice. So we're going to have to subtract, yikes, we're going to have to subtract the A's and B's, okay? Then bear in mind we'll have also counted this section twice, so we're going to take it away, right? B and C. And we will have counted this section twice, but do you see what's happened? Now what we've done is we've subtracted all those away, but we need to add back that center piece that's now missing. Do you see it? This little center piece here. Because we've counted it 3 times, but we've just taken it away. So now we need to add it back, just that little piece. So we're going to add back the A and the B and the C. So that's probably as complicated as it's going to get in this course, but just bear in mind, right? So the formula, when you're expanding it for 3 events, and it's going to just change up ever so slightly, okay? So good luck with your homework, and see you next lesson. Bye.